So, hi. This is going to be the third and final video in this section of the maths to go with the NLS steel structures staircase. I'm going to talk here about bringing it all together in respect to this tread. So we're looking at, I've looked on the internet, and the average weight of male UK is approximately 85 kilograms. So the force acting here in newtons is going to be the 85 kilograms times 9.8 meters per second. So this is going to cause some sort of deflection in the material. And the idea is that there is an equation here that describes this deflection here, which is the force being applied over a length dependent on the material, the Young's modulus of elasticity, and the shape of that material from its inertia, which we've already calculated. Now we're going to take this step by step and redo this calculation, because this equation has to deal with everything in SI units, and as you know, SI units is meters, kilograms, seconds. So we will redo this calculation for the inertia and make sure it's done in meters, and then we'll continue everything in SI units. Now I've done some research, and the suggestion is that for a factor of safety, I think this is a bit high, but one of the websites said that the load, it should be able to cope with a load 5 times the maximum. So if we say, well, 5 times the average is 85, so if you were more than that, if you're going for 5 times as much, we should be well in. So we're going to use that for our force. So what force would be applied? Put the calculator in. So we've got 85 kilograms at 9.8 meters per second. So this would be 833 newtons, multiply that by 5 for the factor of safety. So we need to deal with 4165. So let's go for 4,200 newtons. That's a little bit safer than what we really needed to be. I'm going to go for a round number. So let's go 4,000. The length, well, we decided this was going to be 0.9, so we'll end up with times 0 times meters, and that's going to be cubed. Now we discussed this 48 before as being a calculus number to deal with beam theory, very complicated, not something we need to go into. Again, wait for university for that one, because the maths will give you a headache. This is the Young's modulus of elasticity. So for steel, we're going to be looking at 70 gigapascals, which is 70 times 10 to the 9. Okay, I'm just going to jump to show you where these numbers are coming from. So if I just change my source and switch to the let's just fire up the website. So we're using the hidden staircase structure. That's from a government website. That gives us quite a bit of data. I'll just scroll down through this. So designing for various different aspects of the steel, and you can see the moments of force calculation. The recommendation from this website is that deflection should be no more than 2 millimeters. So I'm going to make a little note up here. So max 2 millimeters. Put a circle around that. That's one of the websites we've been looking at. Now I've linked these all into Teams, so if you jump across to Teams I'll show you where they're all connected. And also, there's an academic paper on the stair safety that I've been reading, and we've got the engineering toolbox for the steel, tensile strength of steel, which is down here. RST, steel, stainless steel, structural 200. Oops. Good for double checking. That's because that is aluminium. I need 200 GPa for steel. Good, worth checking. So we'll So we're going to be looking at 200 GPa, which is 200 times 10 to the 9 for that. And then this calculation for inertia, which was this equation, base height cubed divided by 12. And again, we've got a figure for this from our previous calculation, but actually we haven't got that in meters. So if we just look at that again, the base was 250. Now an easy conversion for you in engineering is, if you've got it in millimeters, if you simply do it times 10 to the minus 3, that will convert it into meters. So I'm going to take that, so I've got 10 millimeters there, do that 10 to the minus 3, and we're going to cube that, and we're going to divide that by 12. And that will give us our inertia in millimeters. So bracket 250 10 to the minus 3 times 10 times 10 to the minus 3, cube that, equals the number that we've seen already, divide that by the 12, and not forgetting, we just slide my calculator across, the engineering notation button, ENG, press that, eight 20.83, so quite 20.8 times 10 to the minus 9, and then we need to take away from that this inner area. Remember that we had to do that before, so we take that away. Remember this was 2 millimeters, so you end up with 246 times 10 to the minus 3 times, take 2 off there, so it's 8 millimeters times 10 to the minus 3 cubed over 12. Clear that. 246 times 10 to the minus 3. Let's put the brackets in, just keep it nice and tidy. Which is going to be times bracket 8 times 10 to the minus 3, because that's millimeters. Cube that. Divide that by 12. And that's given me, now I'll notice this is 10 to the minus 8 here. Again, I'm going to use my engineering button. And that's given me it in engineering notation 10 to the minus 9. So 10.5 times 10 to the minus 9. So we then have 20.8, 10 to the minus 9, take away 10.5, 10 to the minus 9 equals, again, engineering notation. So we're looking at inertia of 10.3 times 10 to the minus 9 meters hypercubed. So that's the inertia I'm going to be using in this equation. So we've got, let's see what the deflection is, and I haven't done this one yet, so let's go for a different colour. We've got 4,000 newtons times 0.9 meters cubed divided by 48 times Young's modulus of steel, 200 times 10 to the 9, put that in a bracket, times the inertia, which in our case was 10.3 times 10 to the minus 9, meters to the 4, like so. I should put pascals in there so we know what we're talking about. Let's crunch some numbers. So we've got 4,000 times 0.9 cubed, try that again, 4,000 times 0.9 cubed, 2916. I just like to work in stages. Okay, let's try this. 48 times 200, 10 to the 9, close the bracket, times, open bracket, inertia, which is 10.3, 10 to the minus 9, close that bracket. The value I'm getting there is 98880. So we've got 2916 divided by 98880 equals 0.0295 meters. That would be 1 meter. That would be the hundreds. That's the tens. 29. That's nearly 30 millimeters. That is too much of a deflection. That would be a step deflecting that much. But remembering that we're talking here about 5 times the load. This now means we need to do some research. The calculations work out, but that's too major a deflection for me to live with. I've got two options. I can stick with the multiplication of times 5 on the load, which I think is really too much, or I can look at, do you remember we talked before about changing this and making this, adding a couple more millimeters here? Yeah. If we added 2 more millimeters there and there, we change that to 12, that might also be a solution. So we might be able to stick with this times 5 load and use the inertia with 12 millimeters on the end here and see what that did to these calculations. Again, that is something I want to leave with you. So I'll probably put together a final solution of what I think, but I'd like you to use these calculations to search through and find out what happens if you reduce this. If we take it from times 5 load, we had 4,000 newtons, maybe you could go down to 2,000 newtons. Maybe that would be more reasonable. So think about doing your research, looking through the standards. What is the UK standard for a staircase? How much of a factor of safety needs to be applied? Is times 5 too much? What would happen to your calculations? Because what the examiner will then see is you using that. Good luck with that. I did say this would be the last video, but I possibly will add one more video with a worked solution, but I'm not going to do that for a while. I'm going to leave you for maybe a couple of days or so, maybe even a week or so, and let you play around with the 3 videos and the maths that you've done so far. See if you can come up with your own solution to this, remembering that we're trying to get to the point where the maximum deflection here would be about that much. Yeah, 2 millimeters, which would be 0.002, something around that. Okay, good luck with that, and I look forward to seeing your solutions.